co-chair of PyData Berlin, and we have here also Theo and Valentina from the PyData Berlin team. As far as I can see, maybe some others.
Daniel, I guess.
Who?
Daniel.
Daniel? Hi, Daniel. Yes, we are PyData Berlin. We are yes, we are the Berlin chapter of PyData, and PyData, as some of you may have heard before, is the educational program of NumFOCUS, and we will talk about it will be introduced very soon. Our program for today is me. I am your introduction happening now. And then we have two very cool talks. One is from Katia Flores Poza, who will talk about controlling many satellites at the same time. And then we will have the second talk from Niladri Shekhardut about deepfake and why he has trust issues. Let's hope he can solve them to some of them today. In between, we will have a 5-minute break, and at the end, we can all meet up in this nice platform called Wonder. It's kind of a spatial chat thingy similar to Gather Town, where you can walk on your screen and talk in smaller groups and chat. And later we will post in the chat the link, so we can all gather there later. This meetup is recorded, so both talks are recorded and are also streamed now in YouTube, so please take it into consideration. For both talks, if you have any questions, please write them down in the chat, and we will pass them on for the speaker at the end of their talk. Also, if you're watching on YouTube, you can also write down the questions in the YouTube chat, and we will pass them on to the speaker. So yeah, as I mentioned, we are PyData Berlin. We are the local chapter of PyData, which is kind of a worldwide thing. We started in 2016, and we had quite a lot of fun meetups and conferences ever since. We are a monthly meetup every third Wednesday of the month. You probably found us on meetup.org, and you can just register and come to all of our meetups. Sometimes these questions comes up. We are all volunteers here, so doing it, not clear why, but yeah, no one pays for that. We have a code of conduct, which is the NumFOCUS code of conduct. In short, be kind to each other, and please remember that the code of conduct applies also when we are online. Yeah, and if you are in Berlin and you are interested in Python and you would like to contact and get in touch with other people who are interested in Python, you're welcome to join the Python Berlin Slack. There's also a data science channel that you can follow, and also sometimes there are job posts there, or you can ask technical problems. Yeah, so we're gonna start now with the first talk. This is us, PyData Berlin. You can follow us on Twitter, and this is our website. I will stop the share now. It is sharing the screen, and I think Valentina will introduce our first speaker.
Yeah, hi everyone. I'm Valentina, also co-organizer of PyData. I have the pleasure to introduce my colleague, Katia, who will be speaking about how Planet operates more than 100 satellites using agile aerospace. Katia is the lead of the space operations team for Planet, and she has a background in telecommunication engineering, but also a passion for space. And she has been working in the space operations for the last 7 years. So she's been scaling operations from starting from 5 satellites to more than 300 satellites launched to date. So, Katia, welcome.
Thanks, Valentina, and thanks to PyData for having me. So let me share my screen. right. Yeah, so I'm going to talk today through what does it mean to operate satellites, and then what does it mean to operate hundreds of them. So yeah, as Valentina mentioned, I'm the team lead of the space operations group at Planet. So we are actually a small team of people, less than 10. And I want to start with showing you what does the constellation that we operate look like. I think a visual way is the best way to do it. Thanks. Right. So this is a day in the life of a dove. So we call our satellites doves because they remind us to that they have 2 wings. So yeah, we call them doves. And then a group of satellites, we will call them flocks. So basically what our sats are doing, they are taking, they are Earth sensing, Earth remote sensing satellites. So they are taking pictures of our Earth continuously, exactly as the simulation shows. So they are acting like a line scanner. So it's like having multiple cameras on the same plane, different planes, just doing that, taking images of landmass as they pass over the Earth. And having that constellation on the space allows us to take daily images of the entire landmass of the Earth. And by having all that data, then we are able to inform decision makers and provide the visibility on changes that happen on the day-to-day that weren't there available before. All right, so I want to give you a quick overview to what a constellation of satellites look like. So we had actually 3 types of satellites. So when I started working on space operations, I was working with the Rapid Eye constellation. So those are 5 satellites, the size of a fridge. And they were launched in 2008, and they have been taking images up to 2020, so last year. So we have this huge archive of data for all these years from this constellation. And of course, even though they were designed to last 6 to 7 years, they outgrow that period of time. So they continue taking images even years after, but it reaches a point where there's such degradation that we wanted to make sure that we had the capability of lowering their orbit so that they could be safely re-enter the atmosphere within a time that is responsible. And then we have the doves and super doves. So we have 2 generations of satellites, and that's why we call them super doves. Super doves are the latest iteration of our sats. So we have launched to date more than 300 of these, and we currently have in orbit more than 180 of these sats. So to give you a sense of the scale, how different these sats are to the Rapid Eye. So the Rapid Eye are like a mini fridge, and the doves are like a shoebox size. So 30 by 10 centimeters, they're very small. But they have very similar capabilities. So they take images, what we call medium resolution. So that means a pixel is equivalent to 3 meters, something that will be 3 meters on ground. And then they image the Earth on different bands. So there are the visual bands that we see, red, green, blue, and then additional bands that will help us identify things like vegetation, vegetation indices that will help for agriculture detection, for example. And then we have a constellation of high resolution satellites. These are, we currently have 21 in space, and these are about the same size as the Rapid Eye, so also like a mini fridge. But these sats have the capability of taking like really high resolution images, so sub-meter resolution. Okay, so that's what we have on space. So it's like having all these cameras around, like orbiting the Earth. So what system do we need to actually talk to the satellite and then make sure that we are getting health data from them and that we are getting all those pictures that they are taking down? So this is in a nutshell what our system looks like. So there's the space segment, which is all this group of satellites. And then we, of course, have radios on board of them so that we can talk to ground stations on Earth. And because we have such a large number of satellites on space, we also need a large number of ground stations on the ground. So operations is not only about taking care of the satellites that are on space, but also taking care of the systems on ground that support the space system. So I'm not gonna go into the detail on the radio frequencies and all, but there are like, to simplify, there are two types of communication. So a low speed one and a high speed one. So with low speed communication, we can get health data from the satellites and upload commands to them. And with high rate radios, then we download, all the images, which are a larger amount of data. And then we need systems that will orchestrate how each of these resources are used, like to which satellites each antenna talking how many times a day, what is each satellite doing on a given day, like where is it taking images, when it's supposed to point to the ground station to download data, when it's supposed to point to the ground and actually take a picture. So those systems are also built in-house for us. So there is a scheduler that will make sure to deconflict those resources. There is mission control. You probably have in mind the picture, like in the latest Mars rover landing, you see like a lot of monitors, each of them monitoring a subsystem, and then engineers behind them, sending the commands and monitoring the telemetry that comes from the spacecraft. So basically that's what mission control does, but in a different setup. So mission control for us is built on the cloud. So, and it doesn't have a lot of people sitting 24/7 in front of them to monitor the sats. So that is possible because we have a lot of automation in place, and I'm gonna elaborate more on that later. But just to have the two differences. So mission control for me is like, now I'm sitting at home in Berlin and I can access it through my laptop, or like from my couch, and then I can command the satellites from there. And then of course we need like a place where we store all the data that comes down. So we have logs, we have telemetry, we have pictures, and we want to make sure that all these systems are built such that we can build on top of them, so that they all have endpoints, that we can query that data with other scripts that will run on top. So those were designed from the very beginning with that in mind. Yeah, and then we have a different, what we call pipeline for the images. That's a different storage where each of the pictures get processed, and there's some quality checks in between. All of that automated, because daily we download more than 15 terabytes of data. So we have to process all that data, of course, in a very automated way. Yeah, and then once the images go through all that processing pipeline and image quality checks, then they get published and delivered on a platform that our customers can access. Cool. So how we do all of that? Of course, this wasn't like the picture at the beginning. So we use agile aerospace on everything, but what does agile aerospace mean? So it's on its core is rapid iteration. So on everything. So from manufacturing the satellites to iterating quickly on the software the satellites are running, on the software that we are running on ground, on how we do testing. So one good example of rapid iteration is these doves. It was actually not just one model. So we have had more than 13 iterations over time. Now we are past 13. So what we do is put some new components, put the new software, launch a new tech demo, test it on orbit, and if that works, then that will become the next version to launch. So that's how we have been able to progress very quickly and get like always the latest and best packed into this 3-unit CubeSat form over the years. And that also happens on the software side. So the way we process the data from space operations point of view to now has changed following that agile aerospace mentality. And a key part of this when trying to do this is also always building the tools with that in mind, with having a scalability in mind, knowing that, okay, now we are operating 20 sats, but in a year we might have 200 on orbit. So that makes things easier and makes the system just robust to handle what comes on the roadmap. And I want to make a pause on talking about Agile to get into something exciting, which is, this is also Agile. So to have that large number of satellites on the space, you need to launch them. And launchers are also, well, now the market is growing, but it's something that constrains, right? There are only enough launchers in the world, so we need to make sure that we are launching as often as we need. So this is just a snapshot of what the year looked like for us, like the last year. So we had launches with 3 different rockets. Oh, sorry. Okay, thanks. Yeah, so we launched from a European rocket, the Vega. There we had 26 of our newest doves, which we call super doves. And then something interesting of that rocket is we had 2 different deployers. So the satellites get deployed from what we call quad pods. So it's basically like boxes with a spring that release the sats. But there were 2 different of those systems on board. So that was something new for us. And then we launched 6 of our high resolution SkySats with SpaceX. We actually had 2 SpaceX launches, 1 Electron, 1 Vega, actually 2 Electrons. So just that's another part that is also Agile, using as many opportunities as we can to get sats into space. And to give you an idea of the amount of data that we have to deal with, the global ground station network last year collected over 5 petabytes of data. And our most recent launch was actually on January. I put this because this was very exciting. So it was a record-breaking launcher. You probably have seen, I don't know if, well, I always see the live transmissions for any rocket launch, but this was a SpaceX record-breaking one because this was the most small sats ever launched all together. So 143 satellites were put all together on this rocket, and they all had the same ride. So here we launched 48 super doves. So also on two different deployers. And this was our 30th successful launch so far. This is one of the images that one of our sats that were launched on that rocket took right after being commissioned. Cool. Now I'm going to talk about how they operate, so the concept of operation, so that you have an idea of what we have to do as a space operations then for automation. So our doves are a monitoring mission. So monitoring means they are always taking pictures over landmass, because that's our point of interest. And then, like, if they are not taking images, then they are talking to the ground stations and downloading that data. And when they are not doing either of those 2 things, to be able to have them as a line scanner separated like in the video, we need to phase them out. So space them out along the orbital plane. And to do that, we use differential drag maneuvers. So like the satellite will be rotating so that the atmospheric drag will affect its position in relation to the others, and they will slowly separate among the plane. So those 3 things. So it's pretty simple. Well, it sounds simple, but yeah, that's basically what the sats have to do. And one important thing to mention is, like, we don't do 24/7 ops. So there's not a person there looking what each satellite is doing all the time. And that's because we have a lot of automation in place. So what we call nominal operations is basically all the tasks to make sure that the satellite is healthy and it's doing what it's supposed to do. So for us, that, it's able to take pictures, and it's taking pictures, and it's able to download them to the ground stations, and it's downloading them. So the first thing of all is, like, how do you tell the satellite what to do? So there comes the scheduler. So the scheduler is an optimizer building house that will every day, score areas of the landmass that each of the satellite can better take a picture of, and then, like, that combined with the power budget of the satellite will just distribute images imaging activities, we call them. So slots where the sats are taking images to each of them and to the whole constellation. And then based on like how many pictures the satellite has taken, so it has a lot of other parameters, and then it optimized for how to better distribute all the available time that the ground stations have. So the scheduler will take care of doing that autonomously. It runs daily, many times a day. So that's one thing. So we don't need an operator or a person like deconflicting or creating schedules for the satellites. Yeah, so that's very important. Also important not only for the space segment, but also for the ground network. So we have more than 40 antennas distributed across the world. So it will be just unsustainable to have, persons dedicated on each of the in each of the locations, and also they have to act as a network. Right? And then we need to know how each of the satellites are doing. So once they are talking to the ground station, that data will come down. And instead of looking at each of that data, and just to give you an idea, our ground stations run more than 2,000 passes a day. So yeah, it needs to be automated. And also the way the images are processed. So yeah, so let me talk about what are our tasks, so I can go more into detail on the automations. So what's a space operation? So from the moment the satellites are manufactured on ground, and then they're put on a rocket, and then they are launched. So as soon as they leave the deployer of the rocket and they are in space, that's where our task starts. So we, as a space ops, are responsible of the commissioning of those sats. Commissioning means making sure that all the subsystems are working as expected, detumbling the satellite. So because when they are deployed, they are tumbling at a given rate. So we want to make sure that we have the attitude controlled, that we check that the radio is working, that the camera is working. So all of that process needs to be done for each of these satellites, and as soon as we can. Right? So for that, we have also built in automations. And actually, this last launch was one of our best commissioning process. So something that would take in the past more than a week to do. So commissioning would last per satellite about 7 to 10 days. We managed to achieve that, to reduce that to less than 2 days. And that's because we built in automation on board and also on ground. So once the satellites are commissioned and they are starting to do what they have to do, taking pictures and downloading, we move into a monitoring stage. So we have to monitor that not unexpected things are happening, that anomalies are being resolved or are being caught. And then at the same time, as part of our agile aerospace, we will continuously test things on orbit. So call them experiments or testings. So obviously we have testing on ground. So we have satellites on ground where we test things first, but we also test things on space. So we have, we call them canaries. So they're like or staging sats, the sats where we will test something first to make sure that everything's fine, and then roll to the whole fleet. And then anomaly debugging, of course. So when something comes up and we need to fix it, we need to look into it. But we are also working towards making this more autonomously. Then yeah, software, we continuously update the software that is running on board the satellite. So that's a big part of testing on ground and also testing on orbit. And then when the satellites reach their end of life, then there is a retirement process. But it doesn't end there. So once the satellite is no longer productive and we have had to retire it, there is a lot of data from that satellite, so from their whole lifetime. And that data will help us create models, degradation models or forecast models, what to expect from next generation satellites. All right, so moving into how space operations change with the amount of satellites. So obviously some years ago we had a tenth, even probably a bit less now, of the amounts of satellites that we have now. Although mission control was built in for scalability, there have been already many iterations. So but the principal feature was that we wanted to have a mission control that will be able to talk to the ground stations and handle the communication with the satellites on its own. So that was a key stepping stone. And then the first satellites that we launched were a way for us as a space operations to learn, like what data we should be looking at. So basically gather operational experience. So initially, what our job looked like was going through reports, so logs that capture things that were happening on ground or things that were happening on board the satellite. And then we'll have some sort of scripting that will filter or group things like similar warnings or similar captures. And then we'll have that summary per satellite. And then an operator, one of us, will have to look into each of those alerts and then understand the root cause and then come up with a mitigation. So we will look at that daily per sat, but of course, as the number of sats increased, that became unsustainable. Yeah, it was time consuming. You need to evaluate every alert. And as we were constantly iterating, there were new things or new features on the satellite. So there were different performance value across satellites. And of course, as the number increased, there was more data to parse through. So I remember there were days where like it took us half a working day to go through all of the alerts. And now it takes us less than an hour. So what changed? So we had to move from the traditional space operations mentality of let's look at what happens with each individual sat to what do we expect from the whole fleet. So we shift that on our minds and say, okay, let's first look at the value of the constellation. So what is important is that as a whole, as a group, these satellites have to deliver this amount of data and they have to download it within this time. So what we look at now is we build metrics with scripts that will aggregate that data for us, and that will be the first indicator if the fleet as a whole is operating as it should. And then if not, then we know there is a fleet-wide issue, and then we have built alerting systems for those metrics that matter the most to us. And we will only react to those alerts then. And then the second layer is identifying the doves or the sats on the fleet that have some non-nominal behavior. But we don't want to do that by looking at each of them. So what we want is for the metrics to tell us, we expect this performance from this sat, but there has been this deviation, and then we just want to see the alert. And we want to see the alert on the specific thing that we have to look at. So that's what we have now. And then the next step is like, okay, now we know this alert on this specific issue has popped up. How do we mitigate this? So once we have the mitigation path, we want that the next time this happens, that we have a script on top. We have a script that detects the issue, and then we have a script that just applies the resolution automatically, so without us knowing. But of course, we want to have visibility on how many times this happens, so we make sure to build metrics around everything, our automations and the performance. So by doing this, we optimize the system availability and the capacity, because there is less engineering time spent at looking at individual things. Investing in automation frees up a lot of our time on that, and then makes the responses way quicker. And so rather than a person looking through something and then there's some delay time between like, okay, coming up with the response and applying the response, the automation is just taking care of that immediately. So that has been a great positive change. So yeah, I talk a lot about metrics. So I mean, this is a very simple diagram of what we have in place as a space operations, but it's basically that. So we have the different entities of the system. So we have mission control that has data from each of the satellites and each of the ground stations. We have orbit data from the sats, we have telemetry, we have logs. All of this data is stored in such a way that we can, that we have endpoints to query that data from. So it's easy for us to build scripts on top. We use Python for this. We have a lot of scripts that, like a group of them that we call mission metrics that will tell us everything from the high level performance of the fleet to like specific performance data per satellite and per subsystem. So it just gives us the granularity that we need, and also it abstracts to true high level metrics. And then we can decide how to use this data. That's the great thing. So we can from there, use those aggregated records and then build automated responses on top, do analysis on Python notebooks, or simply like display the data on visual ways, like using tools like Grafana or Kibana. So it's just like a very powerful way of using data analysis on any issue that can come up. Yeah, so over the years, and I would say especially the last 2 years or so, yeah, the role of the space ops operator has been taken over by the automation. So well, we call it Autobot, but it's not. That's why the logo here. But the automation has taken that role. So it takes care of the common anomalies and maximizes the performance of the fleet. Cool. This is a specific example of one of the automations. This might be going into too much detail, and actually one of my colleagues talked about this specific use case on PyData about more than a year ago now. So maybe it's time for us to do another deep dive on this. But this is just one clear example of where automation is just very important. So we use a job that sets the duty cycle on each satellite. So the duty cycle is how many times in a day the satellite will spend imaging the Earth. So it only can do so much because there's only so much land to take pictures of, and also because there's only so much power. So the power depends, because we have solar panels, the power depends on the sun beta angle. So across the stations in a year, that angle changes. So we want to make sure that our power models and the duty cycle includes that change. So the lower the beta angle, the lower illumination the panels have, so the lower the power it's available to the satellite. So we want to make sure that we know that, and the satellite knows that, so that it's not overdoing itself, like it's not trying to take more pictures with the power that it doesn't have. So this is obviously, it will make sense to do this manually and like checking every time of the year when we have to change this. So basically that's what an automation is doing, is just checking the power telemetry, saying, okay, the voltages on board look okay. If there is a dip and a flag has triggered on the power system, then it will say, oh, you're doing much more than what you need to do. So let's reduce your duty cycle. So it's doing that tuning for us. And by doing that, we are keeping the satellite healthy, and we are also making sure that when we have a lot of power, we are imaging as much as we can, and when not, we are dialing it back. Cool. So yeah, that's just one example of the many things that we have to control, but that are just made easy by having ready available metrics that we can aggregate in any way we can. Yeah, and then build on top of that. So what's next? So we have reached that point where we feel comfortable with, like the detection and mitigation and the metrics that we have. And now we are trying to explore with machine learning applications. So we have all this data already aggregated in many ways. So what we are trying to discover is how we can make use of that historical data altogether. So what we have in mind, like maybe in the long term, it's being able to predict the anomalies. So we know some signatures, we have the data of all the subsystems, we also have operator data when an anomaly has happened. Like as an operator, as a human, what are the things you have to look at? So training those data sets with that might help us be more predictive and also predict performance degradation. So we know, okay, we have a better model for forecasting. And eventually, just having an autonomous fleet. that requires no human in the loop. That's like the ultimate goal, but yeah, we're not there yet, but those are some next steps. Cool. And I wanted to end, because I talk a lot about space and languages, but why is this important? So abstracting a bit from the technical side of things, and actually these are some applications that, where Python or any type of data analysis is super powerful. It's to not to play, but to actually use the data that comes down from the satellites. So to me, this is a very, this is a very powerful video that just shows what can be observed. So this is data from, this is an image from the Amazon forest from 2017 till last year. So, because we have daily images, you can see how things change across time. Yeah, so it's just, I think it's just powerful, and it's something that adds this visibility that we didn't have before. Yeah, you can see there the deforestation, how it's increasing across the days. Yeah, I mean, it's very sad, but yeah, this is a really good example of the impact that our data can make, and of the applications of Earth observation imagery in general. Cool, thanks. Of course, there is some time for questions. I think I might have extended myself a bit, but if you're excited about what we do about space, anything space operations, data analytics, we are hiring a lot, so check out our career pages or let me know if you want to know more. Thanks. So
Thanks a lot, Katya. Was very interesting. I mean, I'm biased, but okay. Will you, Theo or Noah, help me with the questions? We have questions both in YouTube and I guess here.
Please write your question in the chat if you have any. We have a question from YouTube, which what is the lifespan of these satellites from launch to their retirement?
Yeah, so the design life is up to 3 years, but we have definitely seen sats that have lived more than that.
Thanks.
I see a question. Are the images available to the public?
There are 2 different programs. So just recently we signed an agreement with the Norway government. It's called NumFOCUS. So that's opening data for forests around the world. So there are different ways where the data can be shared. I encourage you to visit our website for more info.
Another one.
Yes.
Yeah.
Go on.
Assuming this is open data, are you tracking who is using these images? It will be nice to see the applications.
Well, we definitely have a research program where universities do different studies and like applications with our data, and those are available through paper and scientific publications. I'm not sure if we have that like listed or grouped on our website, but I'm sure if you search for that on the internet, just papers and scientific publications, you will find some of them. No, many of them, not some.
Controlling a walled satellite fleet from a couch is awesome, but does it bring additional security risks?
Yeah, of course. Our security team makes sure that there are all the security measures in place so that we can be able to do this. So it's not as easy as going to the website, for instance, but they make our systems easy to work with for us.
Cool. I think there's no more. Oh, no, yeah, there's no other question. So thanks again, Katya. It was very interesting.
Thanks, Valentina. Thanks, everyone, for inviting me.
Thank you. I think we will have a 5 minutes break if for someone who needs to, I don't know, go to the bathroom or whatever. And then we will proceed.
Yeah, so right now it's 7:47, so let's meet in, let's keep it round, let's meet in 55, if it's okay. So you can all grab a beer if you want, or soda, or go to the toilet, or kebab, whatever you want. Does someone have a joke? No one. Okay, so because we're in PyData, I have to use PyJoke, which is the pip library that you can install. So how to explain the movie Inception to a programmer? When you run a VM inside another VM, inside another VM, everything runs really slow. Still 2 minutes. I really advise to install this library. Really useful. Okay, last one before we go. The child, Dad, why does the sun rise in the east and set in the west? Dad, son, it's working, don't touch it.
That was better, almost funny.
I do my best. Okay, 55. So I think we can start. So let's welcome for the second part with Niladri, who will talk about an overview of deepfakes. So he is working as a data scientist at Sentinel, where he works with government and security agency to defend against deepfakes and information warfare. So Niladri, your turn. You are muted. We don't hear you for the moment.
Yeah, so, sorry.
Yeah.
Can you hear me now?
Yes.
Okay, great. Good evening, everyone, and thanks to PyData Berlin for having me. Today, I'll be talking about deepfakes or why I have trust issues. So let's begin. So one thing I've heard, and I'm sure all of you have heard as well, is that a picture is worth 1,000 words. But what if that picture is actually fake? So then what does it say? Turns out it actually says more. And based on whom and where you ask, it could contain a lot of misinformation. So let's look at this picture. And this picture looks very much like a human, but it's completely fake. And it's been generated by an AI program. So if you look at this website called thispersondoesnotexist.com, so like every time you go there, it will generate a fake image. And turns out that there are a ton of these sites. And based on what you like, I'm sure there's something for everyone, starting from this meme does not exist, this startup does not exist, and also for cat fans, this cat does not exist. So, there's where my trust issues, kind of, begin. So let's look at this deepfake, which has been circulated by, it's becoming very popular this month. And it's a deepfake of Tom Cruise.
That's why. Oh. So, it's a little embarrassing, it reminds me, I was once in Russia, I ran into Gorbachev. He said, Mr. Movie Star, are you nervous? TikTok. You guys cool if I play some sports?
As you can see, like this is the state in 2021, this is what you can do. But it's not all fun. because deepfakes cause a lot of problems. And there was this incident where a journalist was investigating, or rather exposing, a child sex abuse case. And to silence her, they started with the misinformation campaign about some fake tweets. And when she didn't stop, so they launched deepfake porn of her. And that kind of had a very big effect on her. And starting with discrediting her as a journalist, and it ended quite badly. And this is not that uncommon. So you can see a lot of these deepfakes being used to essentially alter public opinion, starting with deepfake of a Belgian premier talking about that climate crisis is imminent and linking that to COVID. And you also have other cases where in India, there was a BJP leader, that is a political party, trying to reach out to their voters in their local language, and the audio was generated, was generated by an AI. And right now, before the entry to use the entry barrier to use deepfake technology was kind of like only experts could use it, let's say. But that has been going down. So we have been seeing the rise of deepfakes as the technical barrier to creating them goes down. So right now, the true estimation is around 100 million plus deepfakes in 2021. And a lot of them have to do with easy to use apps. So there's this very popular app called Reface. You might have heard of it. It actually was trending at one point, it was trending at #1 in entertainment. It also beat TikTok. So it allows you to easily create deepfake videos. And this was a news article which I read yesterday. It was a mother using deepfake to actually frame her daughter's rivals that they were doing, essentially create a fake video of their rivals. So it's, as you can see, it's no longer just being used to defame celebrities or used for political agendas. The next victim could be you or me. So this has probably right now is the tipping point. So the cost of disinformation annually, as estimated in 2019, it was around 78 billion. And the most alarming thing is that false stories actually reach 6 times faster compared to true stories. So the infiltration, if you launch a deepfake, is much faster. So now let's look at a few types of deepfake. So the first one is face swapping. So what happens is that you have a source face, which is the original, and the target face. And the AI model kind of learns what are the facial features of the source and the target are, and essentially swaps these and creates a superimposition to manipulate a face swap deepfake. And then you have the second type, which is facial reenactment. So what happens is that you have the source video and the target. So you can, for example, make facial movements or speak anything you want, and that will kind of be mimicked on the target face. So you could make any person say anything that you want. And this is kind of pretty dangerous, right? You can also have full body deepfakes, where you essentially move the target's entire body to whatever pose you like. And then there's the fourth category, of course, which is audio deepfake, where you can generate an audio which has been mimic a person's voice. So there was this case where a company CEO was, so a deepfake of that company CEO was used to mimic a wire transfer of around $243,000. And this has been a rising problem. So let's look at this video. I'm not going to say to you if this is fake or real. Let's see how you can probably figure this out.
When Mexico sends its people, they're not sending their best. They're not sending you. They're not sending you. They're sending people that have lots of problems, and they're bringing those problems with us. They're bringing drugs, they're bringing crime, they're rapists.
So maybe you know if you've seen this, if it's fake or not, or real. So, and that's where the trust issue really starts to begin, where you even start to doubt what's a real video and you think probably that's a fake. So it's kind of the liar's dividend that we are.
When Mexico sends its people, they're not sending.
And the trust issues start to increase, and probably like to the moon. So there was this report published by a Republican candidate, and he claimed that the George Floyd's death incident was completely fake and digitally manipulated using deepfake. Now, that's of course false, but it's that just because just because deepfake exists, it kind of puts into jeopardy the entire like a real video might be called as it's deepfake. It doesn't exist. You probably just created it. So some of the trust issues are like deepfake can be used to cause fraud, espionage, incite mental or physical harm, like we saw in case of the journalist. And we have been seeing increase in these kind of crimes, particularly against women, where someone says or rather blackmails that a person's deepfake porn might be used. And there are, of course, other aspects to it, like influencing judicial proceedings to the point of actually threatening national integrity and security. So what does the future hold? So right now we have AI generated text. So like there's a very popular model called GPT-3, which can be used to generate any kind of text that you want. And now you have deepfakes to generate any kind of video, or GANs to generate any kind of image. So you essentially have all the tools to generate whatever event you want, and you can do that at scale. And thus you can manipulate opinion and essentially spread misinformation. So how does deepfake work? So one of the most popular approaches used in deepfake is by using something called as autoencoders. So in an autoencoder architecture, there is typically 3 blocks. So one is the encoder, one is the bottleneck, and you have the decoder. So the encoder's job is essentially to encode information like an image, which is a high dimensional representation, into a low representation, or rather encoded, which is stored in the bottleneck. And the decoder decodes that information again to that previous image. So usually the decoder just tries to reconstruct that input. Now with the autoencoders, you can do multiple things. And one of them is you can create fake images or anything you want. So how you can use autoencoders to essentially create deepfakes is that you have this encoder block, which is kind of shared. So we'll actually need 2 autoencoders for creating deepfakes. So so the first part is the top part, which you see is the source image, and the bottom is the target. So the source image is you could be yourself, and the target is that whatever you want to impose, like target person. Let's say you want to swap Donald Trump's image on Alec Baldwin. So Alec Baldwin here is the target, and Donald Trump here is the source. So in this architecture, the encoder is actually the same for both the source and the target. And we have 2 separate decoders. So for the source input, we're going to encode it and again decode it exactly to Donald Trump's image. And for the target, we are going to do the same. And this is what happens in the training part. And when you want to actually generate let's say a deepfake, what you're going to do is, let's say, use the encoder part for Donald Trump's image and use the decoder part for Alec Baldwin's. So what you have here is that by using like the source from the encoder and the decoder part from the targets, you'll essentially kind of swap the faces. Now, this is not exactly like state-of-the-art stuff, because there's a lot of artifacts usually present, And with the previous approach, you would need like pairs of videos. So it would require a lot of training. And you can't exactly use that for like inference or like testing whenever you want. So you would need a lot of data to create someone's deepfake. But technology has been improving since then. So you have this an architecture called as FSCAN, which is kind of subject agnostic. And what that means is that you do not need, a pairwise training. So, so if you do not have a source on a target video, like a training data of it, so you can still use this, because when you actually want to use this sort of architecture to create your own deepfake, you do not need to gather a lot of data and need pairs of source image and target video. So how does this work is by using something called as the generative adversarial network. And the way it works is that you have two blocks. Essentially, one is the generator and another is the discriminator. The generator essentially creates fake images, and the discriminator's job is to try to differentiate between the real images and fake images. And the discriminator does this really well at first, but ultimately the generator actually manages to fool the discriminator into thinking that the fake image is a real image. And by generating these kind of, this sort of a training procedure, we're actually able to create fake images which are very lifelike. Such kind of sort of the stuff which you saw in the beginning, where I showed you an image of a fake person. So how does this work in FSCAN? Is that, for example, if you have the source and you have the target, what you calculate first is kind of like landmarks. So these would be guiding face landmarks. So a landmark is essentially what you see on the left over here. And so it contains points to your face, and it picks out like very specific and important features of your face which can be used to represent. So in this first part, you have these sort of guiding face landmarks, and this will be used to kind of first be passed to a generator to first of all align this source face into sort of the way the target's face is looking at. So the first thing which happens over here is the post correction. And over here, the target's face will be passed to another generator, which kind of separates all these, separates the various parts of the face. So you have the face separated out, and the other parts of the image will be again separated out, like the hair or a earring or something like that. And then essentially we'll be kind of using the landmarks which we got to essentially train our generator to essentially generate images or essentially get sort of like how the movement of the face is working. So we have multiple images. So if it's a video, we can extract multiple frames, and we'll get a lot of these landmarks. So that's why you have multiple landmarks. And once, and if you interpolate between them, you can get an idea of how to move the source, or rather to move the object. So kind of the source's face in a way the target's face is moving. And once you have that, you can do something called as in-painting. So typically, once we have this image, you can see like a lot of parts on this image are kind of not completed. And this is very typical because you will always have partial occlusions. And that can be filled up by an in-painting network, which essentially fills up this image by picking up detail from the target face. So whatever missing features are from the source, we can probably pick it up on the target's face and create something and complete this image. And the last part is the blending part, where the source face is really blended well to the target's face to the point of looking like very real lifelike. And this is open source, so you can try this out. It's present in the GitHub repository of the paper, which is called FSCAN. And they also have a Colab notebook, so you can try it out really fast. So let's look at how you can actually spot a fake image. And this will be a manual procedure. So over here, we can see an image. And this was released by North Korea's Central News Agency. And they were trying to show a military exercise where North Korea's hovercrafts were landing on the East Coast. So and over here, you can see like they have multiple hovercrafts here, and it's actually a fake image. So over here, if you see this left block, and if you compare it with the right block, you'll see that it looks exactly similar. So this was essentially a copy paste of this object over here. And similarly, if you look at a few finer details like this ship, you will notice that there is no wake compared to this ship, where you can see that there's wake. So things of small details, and also like essentially that an image will obviously not violate the laws of physics. You can probably understand that an image is fake. And then there are other things which you can look at, for example, the temperature, the weather data. If the image showcases a particular timestamp, you can probably even see like the sunlight direction where it is coming from. And so the shadows will actually show that. And this is a demonstration of how copy of an object can be copy pasted elsewhere. And over here, you can see that this hovercraft we can copy and I can paste it here. And that essentially showcases a lot of military strength, kind of to mislead other countries. But this is something which can't be done right now, because this is kind of, if you see, for example, the first video of which I showed you of Tom Cruise, it's really difficult to detect deepfake. So, but there's a problem, and so we have a solution as well. And the first is that we can use an image-based model. And so you have this input video, you're going to extract that into frames. And then you're going to extract the face from that frame. So if you look at the entire image, it might not convey a lot of information, and it may not be that useful. So if it's a deepfake video, typically the part which is manipulated is the face itself. So it's better to just look at the face. And then you can use face alignment techniques to essentially rotate that face somewhat so that it's always straight. It just helps the classifier. And then you're going to pass that to a 2D CNN. A CNN is a neural network architecture specifically suited for image tasks. So you can use an architecture like ResNet or an EfficientNet, and then you can finally make a prediction. And this, so you will get a prediction for every frame in that video. And then you can use some kind of scoring strategy to get your final prediction of the entire video. Then you can also use video-based models. So in the previous approach, we used an image-based, so that we were using 2D CNNs. You can also use a 3D CNN. And what that does is essentially looks at both aspects, which is spatial and temporal. So it kind of processes the entire video at one go. And you can, since it's also looking at the temporal aspect, so if there are artifact disappearing and appearing in the next frame or something like that, small changes can also be caught by the classifier. Now, a deepfake detection challenge was hosted on Kaggle. So it was hosted by Facebook, Amazon, and Microsoft. And one trend was that they, like all the top performing solutions, they didn't use digital forensic methods like sensor noise fingerprints, which can extract a lot of information from image creation. When you create an image, it kind of has a lot of information. But if you, let's say, copy paste an object, which like we saw, it will add its own fingerprint noise. and that can be easily picked up. So for example, we have a real face at the top and a fake face at the bottom. And if you do noise level analysis, since this fake photo has been like kind of like essentially a face swap, the part of the face which was swapped and blended, you can see the noise level analysis will kind of reveal that. And it's the same with error level analysis as well. So this can be kind of used to detect deepfakes as well. So there's this paper called Face X-ray for more general face portrait detection. And the good thing is that you don't need any kind of deepfake data set to begin with. So all it needs is faces. And it kind of generates fake faces on its own by essentially blending those faces. We talked about landmarks before. And the way it creates its own sort of fake faces is by, it picks up a random image, it will calculate its landmarks, and it will look for, in the data set, will look for its closest pair of image, which also shares similar landmarks, and it just kind of blends those images. And so what happens is that you created this fake image, and you also created the blending mask. So the blending mask is where these two sort of faces got blended. So that you have the background face and the foreground face, and wherever the part of the image, both the images were kind of blended, you get that final mask. And so you have a pair of mask for every fake image that you create. And essentially, if you have a real image, you do not have a face mask. If it's a fake image, you have a face mask. So essentially what you can do is image segmentation. So an image segmentation is essentially splitting an entire frame into and drawing like a sort of an overlay over each and every object which is different from each other. So for example, over here, you can see a human with a type of overlay and a different overlay on vehicles, for example. So since now we have created our own data set, so keep in mind that our own data set, a fake image will have this sort of a blending mask, and a real face won't show any blending mask. So essentially, you're going to try to predict where that image has been blended. And you can do this using a kind of a U-Net-like architecture, where you have downsampling and an upsampling network. So the final prediction is a fake image if the architecture detects that there is a blending mask, and if it's not a blending mask, if there is no blending mask, it essentially means that the image is real. Then you can also, for example, look at video metadata to essentially detect if a video is fake. And for this approach, you do not need to look at the pixel level. What you instead going to look at is stream descriptors. So every video sort of has some metadata associated with it. And even if some of the metadata tags are missing, you can use something like FFPro to extract all like metadata possible from the video. So, and once you gather all these metadata, and it contains things like what codec it is using, time base, FPS, whatever codec it is using, audio codec, and so on and so forth. And whenever a video is kind of manipulated, some of these stream descriptors change, and it changes in a way which is not kind of correlated or constant with real videos. So by essentially looking at these stream descriptors, you can detect if a video has been manipulated or not. And another strategy is to look at semantic integrity. And what that means is you're going to look at particular features in an image. So if you're given an image, you can calculate a lot of stuff by looking at its metadata, things like GPS and time. So you know the weather data corresponding to a particular time in a particular GPS location. And you can gather all the weather data from it, like sun angles, temperature, humidity, and weather information. And you can also train a neural network to detect all these things on its own. So just by looking at an image, you want to train a neural network to estimate all these values. So, and then you can compare, can you sort of compare the sun angle calculated by the neural network and the sun angle which the weather data shows. And if there is a difference between these two, you can say that this is a fake. If it is kind of the same, it essentially tells that it's a real image. And the last thing which you can do is sort of an audio analysis. So there is something called a spectrogram. A spectrogram can be generated from raw audio by taking its Fourier transform or wavelet transform or things of that nature. So you have this raw audio signal, and you can calculate its spectrogram, and then kind of train a neural network to detect like fake and real videos just by looking at the spectrogram. So the spectrogram is kind of has very sort of peculiar features when audio is generated by AI. And by looking at these kind of features, you can predict whether the audio is fake or not. So our deepfake detection pipeline at Sentinel particularly has been, kind of modeled after cybersecurity standard of defense in depth. And so we have multiple kind of neural networks looking at various features, starting from metadata to semantics integrity and like just image and video-based methods, and also look at the audio. Now, deepfakes aren't all bad. They have their own good use cases as well, which was kind of why they were invented in the first place. For example, you can bring old memories to life. Over here, you can use an app called Deep Nostalgia, which has been vogue of late. So it kind of animates a picture. You can take like any old photograph you have, and it will sort of animate it, which is kind of really nice. Also, like for example, if you want to hide your digital identity, you can do that. So there was this documentary shot of anonymous survivors of the LGBTQ plus community, and this community was in Chechnya, and they did not want to reveal their identities. So some volunteers appeared, and they kind of some people volunteered to allow their face to be swapped on these faces of the survivors to anonymize them. You also have a lot of interesting use cases in Hollywood, for example. So there was, you can see the screenshot of the film The Irishman. And over here, Robert De Niro and Al Pacino's, faces were kind of de-aged. And typically this requires a lot of, first of all, a lot of money and a very big VFX studio. And this is kind of a bottleneck if an indie producer or a small scale production house wants to do these kind of, apply these kind of VFX technologies. But with deepfakes, this barrier is kind of lowered a lot. So there goes to democratizing Hollywood. And of course, you can improve your virtual interactions by animating your digital avatar. So I generated this avatar from a website called Ready Player Me, and then you can kind of animate this face into the way you want to talk. So it kind of improves your virtual interactions in the age of digitization. And with that, I would like to wrap up my talk. And thank you for coming to my PyData talk. I'll be taking questions.
Okay. We have one question from Dimitrios. Does the FSGAN generate ships too? No, it's just for the face, right?
Yeah, it's only for faces, so like deepfake.
We have a question from Veli, but I think it's missing some context. About audio using what data? Can you elaborate on that?
If you have like audio clippings of real and like fake audio, like you can like train a neural network on it. Like the first step you need to do is to essentially get a spectrogram of that audio clip and then just look at the spectrogram. So that be done by a neural network.
Great. Any other questions? Oh, yes. Okay, a question from Stephen. Will the detection method you talked about distinguish between deepfake and more cosmetic or artistic changes? Sorry, I'm not sure to understand the question.
So some of if the data is kind of labeled as a deepfake, it will only like detect if there's a deepfake. So you have like cosmetic changes, it won't be picked up. But if you train a classifier to particularly look at cosmetic changes, then it will be picked up.
We have a question from Ali. Is there a large-scale demand for detecting deepfakes, or other than cases such as Google, Facebook, or other social media?
Yeah, so apart from big companies, there is also like governments and security agencies which need it. So, for example, DARPA, which is the R&D wing of the United States of America, they have they have a lot of funding, and they are trying to detect deepfakes and essentially any kind of video manipulation.
Another question from Fushira. How do you know which portion of a picture frame to check for deepfake?
So the procedure is like you pass in the entire video, and then you can like split that video into frames, and every frame is going to be checked. And now, if your question is to deal like which portions of a particular frame that you want to look at, so typically in a deepfake video, the part which is manipulated is the face. So you can just crop out the face, and then you can look at like particular features. So the way you can extract faces from a frame is by by using some sort of a face detector. So something like MTCNN would work.
Great.
I can see that there's a question if deepfakes are getting harder to detect.
Yeah.
And yes, it is. It's always kind of like a cat and mouse game where the detectors beat the generators, and the generators then again beat the detectors. So we have to improve our detection methods. And as you notice, like we have like there are a lot of ways how you can detect. So and if you kind of utilize multiple methods, it's kind of gets very hard for the generators to essentially make sure that all of these kind of features are taken into account when they're generating.
Great. I think we did all the questions. If you have any more, if you have more questions, we can all meet in Wonder. So we talk at the start. This is basically a platform to be able to interact in smaller group, to have a kind of a more meetup-like feeling. So you will be able to create small group and have a chat about whatever you want. But I will. So thank you again, Niladri, for your talk. It was really interesting. I will stop recording and live on YouTube. On YouTube, if you want to join, you can also go to the meetup page on the PyData chapter. Go to the meetup, and you will have the link to the Wonder if you want to join from there. Okay, I will